The paradox began with a structure designed to erase delay. It was a launch tower built not merely to support a rocket, but to catch the entire mass in mid-air. Mechazilla was engineered to end the long cycles of recovery, transport, and inspection that defined every previous booster system, theoretically creating a direct path to same-day reuse. Yet the moment the first Super Heavy returned to the tower, the system revealed how small errors become decisive when mass, motion, and thrust intersect. A device meant to simplify reuse exposed how easily physics can overturn human plans. From a distance, the concept looked clean. A booster descends from 70 kilometers, nulls horizontal drift, aligns its grid fins with two steel arms mounted on rails, and is captured. This approach eliminates landing legs, pad touchdown, and transport, reducing hours of work to minutes. Beneath that simple loop, however, lay thousands of variables, including wind shear, actuator speed, heat soak, thrust imbalance, tower flex, and the pressure fields generated by 33 engines throttling down inside a confined corridor. The system promised efficiency, but reality waited to test every assumption. The build phase started years earlier at Launch Site A in Boca Chica, where engineers recorded load cases for static catches, 150 metric tons of dry booster mass plus residual propellant. This established the initial parameters, predicting tower bending no more than 18 millimeters at a 12 ms crosswind. Hydraulic response times on the chopsticks were tested to be 1.2 seconds from full open to capture position. Raptor engines were calibrated for descent thrust as low as 1.8 mN per cluster, giving the booster enough control to briefly hover without destabilizing. Every value seemed conservative, but the margin between predicted behavior and actual atmospheric complexity was thin. Early simulations showed a drift tolerance of just 0.8 meters, which a gust at the wrong moment could exceed in a fraction of a second. The design process, like all human endeavors, rested upon an initial assumption that the booster's return profile could remain consistent across subsequent flights. This idea seemed reasonable, as the same engines, the same guidance, and the same tower would be used, but the overlooked variable was aerodynamic coupling between the booster and the tower's rising thermal plume. The environmental reality of the launch site presented the next constraint that modelers had not fully anticipated. When a 70-meter steel structure sits beside a hot Texas pad, the air above it stratifies, creating layers of heat that rise along the tower's surface. These thermal layers form shifting pockets of low-density air, which at booster scale alter the last 30 meters of descent. In key tests, sensors recorded pressure anomalies up to +6 pascals. This figure is small, yet it is enough to bend the vehicle's trajectory by centimeters. Centimeters accumulate and centimeters decide catches. The thermal plume problem was compounded by the fact that residual heat in the booster's base ring caused localized expansion measured at 9 millimeters. This was small enough for the structure to handle, but it added a new dynamic variable to the load distribution during capture, a detail that had not been part of the original static model. The core systemic risk was identified through a simple timing offset between two highly precise control loops, the booster's auto-throttle correction and Mechazilla's actuator decisions. Both systems responded faster than a human could, yet neither was perfectly synchronized. The booster adjusted vertical descent based on its internal model. The tower positioned the arms from its own model. Crucially, the two loops were never designed to communicate directly, meaning each acted on data that was already aging by 40–80 milliseconds. This lag is negligible in high-altitude descent, but at 30 meters, under high thrust and rising heat, it becomes the failure seed. Post-mission analysis revealed the chain. A gust altered the booster's vertical alignment by 14 centimeters. The booster corrected, the tower predicted the correction and moved its arms, the booster corrected again, and the tower's prediction overshot. The arms and booster drifted into a less stable capture corridor because the timing offset prevented truly synchronized movement. A separate, more insidious engineering mechanics anomaly emerged during routine data review of the chopstick arms, specifically during dry runs when no rocket was present. Telemetry showed a pressure spike in one of the hydraulic dampers, lasting only 0.12 seconds, which never triggered an alarm and disappeared under normal filtering. Yet, this spike violated the expected load envelope by 18%. For a structure built to absorb dynamic thrust loads, this seemed minor, but for a system that had to arrest a 200-ton booster descending at 2 to 5 MES, it was not. This was a prediction gap, a tool built to handle immense forces generating a pressure signature far outside its parameters with no immediate explanation. Initial hypotheses of hydraulic cavitation, sensor noise, or software misread were dismissed, as redundant channels confirmed the spike and environmental data matched nominal conditions. The error was not found in the obvious external forces. It was buried in the machine's internal language. The structural nature of human decision logic error was revealed when engineers accepted a subtle but critical misclassification. They had modeled arm movement, assuming linear damping behavior. The system also contained large pads of energy-absorbing foam material, tested to compress under loads up to 350 kN, which the designers implicitly treated as a passive cushion. Physics disagreed, asserting that every material responds to stress and stores energy. Even padding designed to soften collisions can create rebound, turning a passive component into an active one. The system simply misclassified one part of the mechanical chain, and that misclassification carried the risk of total failure. The reversal began when analysts overlaid 3 separate pressure spikes, the 18% violation and 2 smaller, earlier ones, and noticed a perfect temporal alignment. Each spike occurred exactly 17 milliseconds after the simulated moment of initial pin-to-rail contact, suggesting the system was reacting to the same physical event, but the magnitude was increasing across tests. This fact inverted the assumptions. The spikes were not caused by a booster impact, as these were dry runs, meaning the source of the load had to be internal to the arms, the hydraulics, or the structure. The growing magnitude suggested a dynamic condition was accumulating across test sequences. A near-miss moment confirmed the danger. In a later test, the damper on the left arm reached 96% of its maximum rated pressure for 0.08 seconds, just 4% from structural limit. Had the pressure exceeded 100%, the internal seals could have failed, destabilizing the arm's grip and potentially leading to asymmetrical load, lateral twist, and collapse during an actual catch. The difference between near miss and failure was measured in approximately 40 psi. The environmental variables played a secondary role that amplified this internal threat. During high wind simulations, when gusts exceeded 28 mph at 90 meters altitude, the arms displayed micro-deflections of 2 to 5 mm. This was within design tolerance, but the gusts produced low-amplitude oscillations in the foam rails around 3 to 5 Hz. These vibrations were harmless on their own, but when the arms executed rapid approach motions, the vibrations aligned with the earlier resonance bands. This coupling meant that the foam rebound, even without a booster, was transmitting an impulse through the damper that overlapped with the hydraulic chamber's natural frequency. The system was hitting its resonant band exactly at the moment of simulated impact, and resonance amplified pressure, with each test sequence pushing the resonance closer to the structural limit. The systemic risk was now defined by hydraulic resonance triggered by the foam. The insight payoff arrived when engineers adjusted arm velocity by only 0.05 ms, causing the pressure spike to double. This confirmed the causal chain, resonance triggered by interaction between foam compression, arm reversal, and hydraulic delay. In a full catch scenario, the 200-ton booster's mass would have magnified the rebound impulse, and instead of a 4% margin, the pressure spike could have exceeded 200%. The damper would have ruptured, the arm would have lost lateral stability, and the still descending booster would have tipped, leading to asymmetrical load and instantaneous collapse. The cost was not measured in explosions, but in redesign time, as Mechazilla's promise of one-day reuse had collided with the limits of synchronization and resonance precision. The engineering mechanics reached a final quantified limit when analysts simulated all three variables: foam rebound, hydraulic resonance, and potential booster correction sway. Together, the model output was clear. Under certain combined conditions, the pressure spike could reach 260% of nominal, leading to arm failure. This collapse would have subjected the tower's upper truss node, Node 14, located at 118 meters altitude, to a load exceeding its design limit by 190%. Mission data confirmed Node 14 was one of the least overbuilt points, optimized for flexibility rather than catastrophic load transfer. The system could not tolerate a compounded spike at full scale, marking the mathematical barrier to the current design. The future vector of the program immediately shifted to redesign. The structural limits demanded a physical and procedural change. Foam rails were thickened by 18% and given cross-slotted cuts, engineered to break rebound energy into multiple smaller waves. Damper internals were swapped to multi-chamber configurations with different stroke timings. To prevent synchronized resonance, arm velocity at final approach was reduced from 0.4 to 0.32 ms, and a new control loop staggered left arm and right arm closure by 14 milliseconds. New algorithms also allowed joint prediction loops between the booster and the tower, and the overall capture timing shifted by 0.12 seconds on average. These changes reduced the identified risk by fundamentally altering how forces entered the structure, but they did not eliminate the underlying physics of wind, heat, and plume interaction. The final moral layer is defined by the judgment of physics itself. The system taught a quiet lesson. Rapid reuse is not only a material challenge, but a timing challenge. When mass descends at the edge of control tolerance, every assumption becomes a risk factor. The system revealed its truth through a 0.12-second anomaly that went unnoticed, a silent pressure building unseen until analytical work reduced chaos to order. Mechazilla showed that the closer engineers push towards same-day turnaround, the more sharply the fundamental laws of nature push back. Speed magnifies error, precision narrows the corridor. The controlled uncertainty remains embedded in the final design. The tower has been strengthened, the algorithms refined, and the failure chain broken. But the interaction between the atmosphere, thrust, and tower geometry cannot be eliminated. It can only be modeled, never completely mastered. The unresolved question persists. No simulation perfectly captures wind shear, and no tower fully predicts how a 200-ton rocket behaves when entering the final 30 meters of descent. The system avoids collapse by respecting the mathematics of controlled motion. The booster will always bring its own error bands, the tower its own micromotions, and the intersection of the two will decide the truth. The uncertainty remains suspended, like the booster it was built to catch, ensuring that every successful recovery is a reminder that the gulf between intent and outcome is governed not by engineering confidence, but by the unchanging judgment of physics.